Schedulers decide who runs next, and the Pattern Mastery 100 Essential Task Scheduler tests if you can translate a real-world CPU cooldown rule into tight math. Interviewers love it because brute force simulations get messy, but an elegant counting plus formula nails it in one line. Let's master it with BASIC and ship an optimal solution in minutes. Let's break this down. We're given a list of tasks labeled by letters, for example, A, Z, and a cooldown N. Between two runs of the same task, there must be at least N idle intervals. We must compute the minimum number of intervals, tasks plus idles, to finish all tasks. Now let's assess it. A priority queue simulation works but is overkill. There's a clean formula. Let max be the maximum frequency among tasks, and num_max be how many tasks achieve that frequency. We build max 1 full frames, each of length n+1, task plus cooldown slots. The final layer places the num_max most frequent tasks. The answer is max len tasks, max, 1, n+1, plus num_max, because if we have enough other tasks to fill idles, total time is just len tasks. Here is the structure. Plan, count task frequencies, compute fmax and num_max, then apply the formula and return the max with len tasks. Handle edge cases like tasks equals. Now let's implement the greedy heap-based simulation, repeatedly scheduling the most frequent tasks while respecting cooldown gaps. We import heapy, which gives us a priority queue, perfect for always choosing the most frequent task next. We also bring in collections, so we can use counter to count task frequencies easily. We're defining the solution class that will compute the least time needed to finish all tasks. This method receives the list of tasks and the cooldown time n, and must schedule them with minimal idle time. We count how many times each task appears. This gives us a frequency map, almost like knowing how many copies of each job we must process. We convert each frequency into a negative number. Python's heap is a min heap, but using negatives makes it behave like a max heap. We turn our list into a heap so we can always grab the task with the highest remaining frequency. We start a global clock that counts every passing unit of time, tasks, or idles. This queue will hold tasks that are cooling down. Each item is release_time, remaining_count. We keep going as long as there are tasks to run or tasks waiting to cool down. Each loop iteration represents one time unit passing. If we have tasks available to run right now, we pop the most frequent task, the negative number with largest magnitude. Because this is stored as a negative, adding 1 moves it closer to 0, meaning we've used one occurrence of the task. If the task still has more remaining occurrences, we push it into the cooldown queue with the time when it will be allowed to run again. Current_time plus n. If the earliest cooling task is now ready to run again, we remove it from the queue. This task is available again. We push it back into the heap so it can be scheduled on future cycles. When all tasks and cooldowns are done, our clock tells us exactly how long the schedule took. And that's how this algorithm works. It first counts how often each task appears, then simulates time using a max heap to pick the best task and a cooldown queue to manage delays. Accurate, greedy, and wonderfully intuitive. Let's check. These are CPU tasks where each same letter must have at least 2 time units of cooldown before it can run again. With a greedy heap simulation, we always pick the task with the highest remaining count that isn't in cooldown, and insert idle slots only when no valid task is available. A valid schedule, one of several, is A, B, idle, A, B, idle, A, B. All 3 A's are spaced by at least 2 units. All 3 B's are also spaced by at least 2 units. Total time slots equals 8. The computed timeline length matches the expected answer, so the heap-based simulation is working correctly. Now let's implement the counting approach, using frequency analysis and a direct formula to compute the minimum required intervals without simulating the timeline. We import collections so we can use counter to count how many times each task appears. We define our solution class that computes the minimum time needed to finish all tasks under cooldown constraints. This method receives the tasks and the cooldown n, and returns the fewest time units needed to finish everything. We build a frequency map of all tasks, essentially counting how many of each type we have. We find the maximum frequency, the number of times the most common task appears. This number dictates the structure of our schedule. We count how many task types appear exactly max_freq times. There might be multiple tasks tied for most frequent, and we must account for them. We create max_freq, 1 gaps between these highest frequency tasks. Think of the most frequent tasks as forming a skeleton with slots between them. Each gap has a certain size. We start with n cooldown slots, but if multiple tasks tie for most frequent, they fill some of those slots automatically. So we subtract count_max, 1, To compute the leftover empty positions per gap, we now compute the total number of empty slots across the whole schedule frame. We count how many tasks are not part of the most frequent category. These tasks will fill the empty slots if possible. If we still have unused empty slots after placing all remaining tasks, those leftover slots become mandatory idle cycles. If we have enough leftover tasks to fill everything, idle time becomes 0. The total time is simply number of tasks plus number of required idle cycles. This gives us the minimal possible timeline. And that's how this algorithm works. It first analyzes task frequencies to identify the scheduling constraints, then uses a mathematical formula to calculate exactly how many idle slots are unavoidable. No simulation needed. Clean, fast, and elegantly optimized. Let's test our function using these tasks. Each letter represents a CPU job, and n equals 1 means identical tasks need at least one cooldown slot between them. We count how often each task appears. A 2 times. B 2 times. C 1 time. D 1 time. The most frequent tasks are A and B, both appearing twice, using the task scheduling formula. But since we have 6 total tasks, the schedule can simply fit all of them with no idle time, giving us 6 units. And that's exactly what our program outputs, 6. The result matches perfectly. So, our implementation is correct. The counting formula efficiently computes the minimal schedule length and behaves exactly as expected. Schedulers decide who runs next, and Task Scheduler turns that real-world CPU rule into math you can master in minutes. It's a brilliant test of logic, counting, and optimization. Let's do a recap. We're given tasks and a cooldown value n, meaning identical tasks must have at least n intervals between them. The goal is to find the minimum total intervals, tasks plus any necessary idle time. While simulating with a priority queue works, it's not efficient. The elegant way is counting. Find the most frequent task, fmax, and how many tasks tie for that frequency, num_max. Use a formula that accounts for full frames of cooldowns and then fills remaining slots. The plan. Count frequencies of all tasks. Compute fmax and num_max. Apply the formula, max total tasks, max, 1, n plus 1, plus num_max. This gives the minimum time with no unnecessary simulation. We executed this logic cleanly, counted frequencies, applied the formula, and ran the code successfully on LeetCode without any errors. All test cases passed. The math perfectly matched the scheduling outcomes. The big takeaway, math beats simulation. Once you spot patterns in frequency and gaps, scheduling problems become pure arithmetic.